Okay, joins have stabilized, so we're going to go ahead and get started. I'd like to thank everyone who's joining us today. Welcome to CNCF's webinar, How to Make Kubernetes Autoscale Work, Novice to Pro to VIP with Real Multi-Tier Microservices. My name is Josh Burkus. I am a CNCF ambassador, and I am Kubernetes Community Manager at Red Hat, and I will be moderating today's webinar. We'd like to welcome our presenters today, Meng Ding and Enlin Xu from Turbonomic, who are going to be presenting on autoscaling. Before we get started, let me explain a little bit of this for those of you who haven't attended one of these webinars before. First, during the webinar, you will not be able to speak as an attendee. You are muted. There is a Q&A box, question and answer box at the bottom of the Zoom application. If you have questions, please drop your questions in there, and we will get to as many as we can at the end, or if the presenters decide to pick up some of the questions before then. Keep in mind that this session is being recorded and will be sent out afterwards with a link to the presentation. But you do also want to keep in mind that we're being recorded when you ask your questions. With that, I'm going to hand this over to Meng and Enlin to kick off today's presentation. So please tell us how to make autoscaling work.
Thank you, Josh. This is Enlin, and together with me is Meng Ding. So we are coming from Turbonomic. Just want to make sure, can you hear me okay?
Yes, you're coming through loud and clear.
That's great. Thanks, Josh. So as Josh mentioned, that we are going to share our experiment on how to make Kubernetes autoscale work. So I don't know how many people have tried different autoscaler technologies provided by Kubernetes out of the box, and do you think it's easy or it's difficult to configure it? But in any case, we want to share our experiment on our testbed, which is based on the real multi-tier microservice-based application, and share some lessons we learned with everyone. Hopefully, you will feel it useful. So a little bit introduction about ourselves. We understand that this is definitely not a vendor pitching session, but we really want to tell you who we are, and you can decide whether you want to trust us or not to trust us. So Turbonomic is founded in 2009, headquartered in Boston. And we have now more than 500 employees. We are one of the CNCF Silver member, and in the upcoming KubeCon Europe in Barcelona 2019, we're actually one of the platinum sponsors of KubeCon. So if you happen to go there also, I think it will be much easier to find us compared to the past when we were silver sponsors. And the whole idea of the software that we provided is that software should manage your IT resources, not people. So basically, we provide an abstraction and a common analysis engine on top of the abstraction to help you to manage your IT resources, most efficient and most productive way to increase your application performance. So just like what Kelsey Hightower put in his Twitter, here's my application, run it for me, when and where I want it securely. That's the end game. So our goal is to provide you the experience of the end game, so you don't have to manage your data center manually all the time. So next slide, please. So container adoption is accelerating. What a surprise. So I'm pretty sure that the reason why you joined is because you're at different maturity curve, different stage of adopting the containers. So this is actually a survey our marketing team did among more than 2,000 of our customers, and if you can see, the sample size of this survey is about 600, around 700. And based on the response we get, we expect to see 165% growth in the next 18 months. So this is not a surprising, I think. So container adoption has been accelerating over the past few years, and that's the same we get from the survey that we look at. So among them, 43% of their environment will be running containerized application within the next 18 months, and actually 26% of their environment run containerized application today. Among what? 28% are mission critical. So which means that application performance is really, really important to these people because it directly impacts their business. Next slide, please. So where are they? In terms of maturity curve, we can see people who's playing with different technology, they actually are at different stages of how they adopt the container, from exploring, like how do they contain. So you can actually find a more interesting trail map that is coming from CNCF directly at different stages. Like you start to look at technology to containerize your application, what is the runtime, and you start to do some CI/CD exploring, how to package, what is the image registry, something like that. Then later you start to consider, when you have a certain scale of deployment, you start to think about what orchestration platform you should use, Kubernetes versus Cloud Foundry versus Mesos, all the Docker Swarm, for example, right? And based on some of the conversation I had with some of the biggest banks in the world, in fact, I heard a lot, I want to focus on the 6% that is showing here. A lot of people actually told me that the platform first strategy, which is basically the new standard, especially for the greenfield application, the new standard is every application has to be run in container, which is actually prior to even, there's several parallel things ongoing together, right? Some people is looking at which container technology to use, which orchestration to use, but at the same time, high level up, people are deciding that for ongoing basis that all the greenfield applications should be packaged in container. That basically tells you how promising this containerization trend we are seeing at this moment. So let's back to next slide, please. So let's back to the question, containerization, why? Is it because Docker is cool? So part of the reason why, so that's too quick one, but that's okay, thank you. So Docker is actually cool, but Docker is definitely not the inventor of containers. So things like LXC appears much earlier than Docker, but Docker did bring a lot of convenience to people who want to use containers, bring containers, the experience of using container to a different level. It's much more user-friendly now, but the reason behind the containerization, that revolution, is definitely not because this is so cool that you have to adopt it. And also, is it because container is lightweight? Since you already see the answer is no. Yes, it's funny. A few years ago, when you start to educate container to people, you always see a comparison chart between a container and VM, because that's just where the two units get a lot of similarity, different points, and how we differentiate them. But in fact, yes, container you don't have to install operating system. That's mostly the highly visible item compared to VM with container. But is that the motivation why people want to use container? The answer is no, because think about your huge data center. You have a lot of resources there. And what is the operating system going to take you? The overhead is not that big to motivate people to start to adopt container. So that's also not the main reason. So is container is cost efficient? As you can imagine, the answer is also no. So apparently that container, you can run container on bare metal, which may eliminate some of the tax of virtualization that you pay to these virtualization vendors. But we also see a lot of people, they run containers inside their virtual machines, which means they're still going to pay the tax of virtualization. So whether or not this actually saves the cost or not is another question, depending on how you actually design and architect the whole IT infrastructure. But definitely that's also not the reason. So what's the reason? It's all about applications, right? So it's all about how do I scale my application more properly on the fly? How do I make my application more portability? So with the help of Kubernetes, you actually install your Kubernetes, which serves like an abstraction for different IaaS options. You can do application deployment, lifecycle management on the same platform, regardless what kind of, whether you use on-prem, public cloud, or a mix of two, multi-cloud. You can actually run applications in a uniform way. And also you want the elasticity coming from the full stack, right? You want elasticity on the application instances. You also want the elasticity at the cluster level so that you can scale up and down your resources. That containerization definitely gives you the flexibility that you can have all these benefits. And once you actually structure, re-architect your application into microservices, put them in the container is a no-brainer option. So that's the real motivation, the real reason behind the scene why people start to adopt container. So what does container do here? Unfortunately, that's it, packaging and distribution. Again, so you can choose not to believe me, but in fact, this is not coming from me. If you check, month, please give another click. Yeah, thank you. So Kelsey Hightower actually, sorry, I keep copy and paste his Twitter. So because this is, we are highly, the vision, the value-wise, we are highly aligned. So Kelsey Hightower mentioned that back in December 2017, people will soon learn that containers only solve the software packaging distribution problems. Containers don't manage anything, they need to be managed. So if you associate, let me do a quick summary of the previous few slides. That's okay, well, we can go to the next slide. If we can quickly go over the past few slides really quickly. So people are adopting containers and people are actually deploying their mission critical application into their containerized environment, into their container platform. But to assure that this business application, mission critical business application perform as they expected, never actually violate any kind of service level objective or service level agreement, that's not easy, right? Containerization doesn't help you with that. Portability, scalability, and elasticity. Imagine that now you have application that is in smaller pieces, but still your Java application is still going to be Java application. You still might need to manage JVM. You still need to manage JVM now in each microservices. Originally, you may have one VM that runs everything monolithically. Now you have tons of containers that is break down into microservices for you to easily to scale them up, deploy them different places. But on the other hand, to actually manage the performance, to manage the efficiency of how you run these containers becomes more complexity. Why? Because you have a much higher density and more layer to manage, just like from the left to right. So that's the complexity. So having said that, that's why the upstream Kubernetes also try to come up with some linear, some out-of-box solutions for different layers of your stack. For example, how do you vertical scale your container? How do you horizontal scale your pod? How do you scale up and down your clusters using Autoscaler? So different scalar options, how to use them, how do you actually manage them is maybe one of the solutions that you can actually manage this complexity. So without saying much, I'm going to hand it over to Mon to continue and share all the experiments that we have done using the autoscaler that provided by Kubernetes. Mon, please take over from here.
Okay, thank you very much. Can everyone hear me?
Yes.
Yes. Okay, thank you. So my name is Meng. I'm a software engineer with Turbonomic. As Elena just said, in a container world, assuring performance and maximize resource utilization is a very difficult problem. It's a hard problem. And Kubernetes does offer auto-scaling solutions on different levels, but we feel that there is limited information in terms of how to make best use of these solutions and then apply them to a real multi-tiered microservice applications. So that's the purpose of this webinar. We did some experimentation and we want to share with you guys our efforts in answering all those above questions and the lessons we've learned along the journey. So as many of you must have known that Kubernetes offers auto-scaling solutions on different levels. On the pod level, there are HPA, which is horizontal pod autoscaler, which is the most secure, mature and easy to enable solution. Another solution on the pod level is the vertical pod autoscaler, which is still evolving very quickly. And it's an add-on solution for Kubernetes. And we'll talk about the pros and cons of these solutions in the next slide. On the node level, there is the cluster autoscaler solution, which is used, for example, it can decide when to scale up, scale out the node or scale down the node based on the pending pods or the node utilization in your cluster. So imagine you have these many options that you can choose from and how you can utilize them in the best and most efficient way is definitely a non-trivial task. For this particular talk, we're going to focus on the horizontal pod autoscaler solution, because that is the most mature solution, and I think most people are trying to use that and get familiarized with that. So just a quick talk on the solution itself. It's a very high-level overview of the HPA and VPA solutions. So this is an overview of HPA solution where it is built into the native Kubernetes control loop. There is the horizontal pod autoscaler that is monitoring the metrics periodically and make decision to scale up or down the number of replicas of your deployment or RC based on a threshold-based algorithm. And the metrics that's being watched can include the usual CPU and memory, but it also support, which is very nicely, the custom metrics, things like response time and QPS, network traffic. These metrics can be supplied by third-party vendors. It can be nicely integrated into the system, and also external metrics. On the VPA side, as I said, it is still a fast-evolving solution in the community. The idea is basically, again, to monitor the metrics, which is CPU use and memory use value, and use that to update and resize the CPU and memory requests for each pod in your deployment. Of course, there is some downside of the solution for now. The VPA at this moment is still disruptive. In order to update the resource request, pod needs to be killed and restarted. I believe there are effort in the community to enable the in-place resource update of the pod, which could be very handy when that's implemented. So in order to evaluate the Kubernetes autoscale solution, we have created a non-trivial testbed because we believe that it's the only way to be able to verify the solutions and to test the pros and cons. So the application we have created in-house is a real microservice-based applications with multiple tiers. So we have the HTTP front-end API service backed by multiple gRPC services. The whole application is like a Twitter-like application. Basically, multiple users can tweet and make friends, things like that. And everything's backed by the Cassandra database. The deployment of the testbed, as outlined in this slide, the service we just talked about, of course, we installed Istio and injected proxy into the pods. Istio is mainly used to load balance the HTTP and both HTTP and gRPC traffic, and also to do the metrics collection and reporting. Cassandra is deployed as stateful set. So this is the flow of our testbed. So how we put everything together. The blue box illustrates the Twitter app, and we've just talked about. And the orange box is the Istio service mesh deployment, and which provides all the functionality I just talked about, and also, of course, very importantly, the visibility through the Grafana dashboard. And the green box are the metrics servers. This includes the default metrics server that is used to collect the CPU and memory usage, and also the custom metrics that is very important for experimentation to collect custom metrics like response time and transaction. And of course, these metrics server can be accessed through the Kubernetes API aggregator framework. So to basically to unify the endpoints. And finally, the user simulator is is achieved by launching a locus cluster. We use the locus cluster to simulate user workloads. You can specify different patterns and different numbers of users. So we will present our results a little bit later. So with this, that's been said, so we have our testbed in place. The next thing is how are we going to design our tests? What kind of, how do we enable these solutions? So what is the steps that we should go through? Naturally, we think that the easiest step would be to use the CPU-based HPA because that is readily available. All you need is to install a metric server and that supply the metrics that is needed, and you just run a few commands to specify the parameters. But the difficult part for us is, you know, as many of you may experience when you try to tune an application, is that you don't really know exactly which tier is your bottleneck, and you don't know which particular deployment to scale, and to how many replicas to scale to, and how do you specify your threshold. Of course, we don't know in the first place either. We just make a guess. So I think CPU percent 75 is a reasonable guess. Any number higher would be, you know, probably cause performance degradation. Any performance lower would probably cause resource wastage. And also we don't know what the maximum number to set. We just set up 10 as a safe number. We're just going to experiment. And of course, we would enable them for most of our Twitter services. That includes the API, the tweet, and then user services. We run these experiments, and of course, we can collect the metrics and show them in the Grafana dashboard in a very nice way. As you can see here, we launch the workload on a locus cluster where we simulate 300 users that make requests to the Twitter service at the same time. The workload starts at 7 o'clock and ends at 8 o'clock. It is constant workload. As we can see from the graph we collected from all the metrics, of course, is collected from Prometheus and illustrated, shown on the dashboard. When the load suddenly comes at 7 o'clock, the response time spikes to a very high number, which is not shown here in the graph, is the CPU utilization of the pod also starts to increase. I need to mention that initially every service has only one pod. As you can see here, API, friend, tweet, user, every service only has one pod. With the onset of the workload, we can see that the CPU-based HPA kicks in. And the number of pods for the API service and tweet service gradually spins up. It takes about 10 minutes for the whole thing to stabilize and for the response time to go down to an acceptable level, which is around 200 to 300 milliseconds. And we can see that with the effect of HPA based on CPU utilization, the number of tweet and API servers, the number of pods stabilize as 4. So this is encouraging, as we can see that when the load stabilizes, and HPA based on CPU is able to maintain an average CPU utilization across the whole cluster to be around the target threshold, which is 75%. The downside of this approach is that we see that with the onset of workload, the spin up of the pods is a little bit slow. It takes almost 10 minutes for the whole system to respond to the workload. This is a little bit undesirable. But this is also explainable by the algorithm, right? So initially you have 75% as the threshold, and the CPU can only goes up to 100%. So the number of pods can only increase by 1. So that's explained how the whole system, how it works with the CPU-based approach. So now we think, okay, what can we do to improve this initial slow response to the increase of the workload? We think naturally, if we can use response time as our metrics to monitor, because we know that when the workload suddenly increases, the response time goes very high. If we use the response time as our custom metrics and we do HPA based on that, we must achieve very good results in terms of fast response to the workload, right? So that's what we trying to do next. But it turns out that to enable custom metrics based HPA requires a little bit of work. So first of all, we need to deploy the SDO metrics to collect the response time and which is the same as latency and transactions, whatever custom metrics you want to collect, right? And then we install the Kubernetes Prometheus adapter, which is an open source solution, which is, I believe, is the most popular open source solution for this particular use case. And we define the metrics collection rules for the Prometheus adapter, such that we are able to, such that the Prometheus adapter is able to collect and expose this metrics endpoint. And after enabling the custom metrics server, and we create an HPA based on the response time, this is only enabled through the Autoscaling v2 beta 1 and up API versions. So as you can see from the configuration file that we are going through so basically we specify the object type and we specify our average response time, which is collected by the Prometheus adapter. We, in fact, did not know what the max number of replicas to set initially. And apparently we did a lot of tuning and experimentation. And with the next slide, we can see the result of when we define the maximum number of replicas to be 15 for API and tweet service. We see that there is a very undesirable effect of ping pong where the number of replicas was spins up, in a large number of, was spin up quickly, and also when the number of replicas spins up quickly and the response time suddenly, lowers, and then it goes to the undesirably low number, which causes the scale down of the pod again. So you see this ping pong effect, which is really, really undesirable. And we have tuned the number of replicas. We tried from number 4 to 15, the ping pong effect is always the same. So now this leads to us to think, what if we can combine the solution of the CPU-based HPA and the response time-based HPA? If we combine them together, that may provide an opportunity to not only maximize the resource utilization, but also respond to the sudden increase of load very quickly. So this is the next experiment we try. Because we already implemented the custom metrics server, so it's just a matter of defining multiple metrics in the HPA configuration to monitor. And of course, we need to specify the target value. The target value is obtained. Actually, it takes some time to understand the characteristic of nature of the application, and we realize that we cannot specify a random number of the maximum replicas. It doesn't necessarily make a better result if you specify a larger number of max replicas. The number of max replicas we specify is based on the CPU-based HPA result, and we know through the previous experiment that when the whole system stabilizes, the max number of treated API replicas is around 4 to 6. So that's why we specify the max number of 6 here. And also we got the value of response time in a stabilized environment, and we specified that as the threshold. So as you can see that the number is, because of this iterative experiments, we understand the characteristic of the application, we are able to supply it with a more reasonable a number. So as you can imagine, with all these implemented, we are able to achieve the best results out of the 3. So first of all, when the load increases, the constant load increases at 1700, we see, of course, there is a sudden spike of response time, but of course, because of the response time based HPA, the number of pods spins up very quickly. And because of also, we didn't set a very large number of max replicas, so it also sort of stabilized at 4 to maximize the CPU utilization. And we also see the effect of the response time, lowers much more quickly. In about 3 to 4 minutes, the response time lowers to around 300 to 400, which is in a defined and predefined range. So this is very encouraging results, and we, given with this particular configuration, we apply this to a different varying workloads. So when we change the workloads, basically at the locus cluster side, we tune and change the number of users coming in. And with this combined CPU and response time based approach, we are able to achieve the results as expected. So this are the iterative experiments that we've been through. Of course, we pick the most, we pick those experiments that, that illustrates our point the best, right? Because of course, when we actually did the experiments, we did many more rounds. And it really is a very time-consuming exercise, including understanding the custom-based HPA metrics, settings, configurations, to all the tuning of the replicas and defining and finding the bottleneck in the multi-tiered applications. So I want to talk about the takeaways from our experiments. As I've just mentioned, the upstream Kubernetes HPA solutions, Autoscale solution does work, but not before you spend a lot of time setting it up and then tuning it. And I've outlined the many of the steps that we've been through, and every step is also very time consuming, but of course, if you've never been through the whole exercise and journey, it could be a little bit daunting, but after you have been working on it with a particular application, you get the basic idea, and then it will be much easier for you to continue to tune. Of course, it does require multiple experiments to determine the best set of configuration and threshold. Overall, it is a threshold-based algorithm, and it is up to the user and the man to find out the best, the number to tune. And another takeaway is, again, we've mentioned that it is very difficult. It's not an easy task to assure application performance. Because what we see is only a symptom, right? You have slow response time, you have low transaction QPS. So we have many dimensions to explore. Shall we use horizontal scale, or is vertical scale a better options? When we vertical scale, what is the capacity we want to scale to? Will we have noisy neighbor issues? Do we have the visibility of the entire stack that the application is running on? Are there any underlying infrastructure congestion that we are not aware of? All of these combined to make it very difficult. And what about, this is only just one application we're talking about. What about, you know, many microservices in your application? This is becoming a trend, right? Many companies are decompose their monolith application and pretty much rewrite from ground up to make microservice based. It could become very complicated, and it's going to be a very interesting exercise for everyone to implement the HPA solution in a real environment. So with that, that's pretty much I want to talk about and share for this particular session. I wasn't sure if there's any questions.
Thanks, Mon. Actually, we received quite a few questions in the Q&A panel, and I went while Mon is talking, trying to type my answers there. So since we have enough time to go over the Q&A, so I will just go over all the questions that we received from the audience, and hopefully, first, thank you so much, Mon, to share the experiment. I hope this people find it useful, because for us, we do find that even though HPA sounds really promising, and it looks like you only need to configure min replicas, what's a target utilization, it seems easy enough, but in reality, it's not so easy, because you have a lot of metrics to choose exactly which one you should actually scale the application. And it's really a case-by-case scenario for different types of application, for databases, for web servers, for machine learning applications. So everything can be different. And we are not saying that we have the best practice here. Please bear in mind, we are just trying to share what we did with a web server, treat like web servers, and how even though this application is simple, HPA sounds simple, but to use HPA against this simple application is not actually that trivial, as Mon said. And the good news is everything we did is actually open source. You can actually find the testbed with all the YAML file. You can deploy the testbed yourself. You can deploy the locust yourself and start to simulate, play with it. Also, you can apply the same methodology on your own applications, use the same load simulator on the same on your own application, and try to play with HPA and see if that is so easy to configure. How do you actually configure min replica, max replicas, and target utilization, and do you achieve your SLO or not? So yeah, so one of the questions, so let me just read aloud the questions. So Josh, should I just read aloud the questions and share the answer with everybody?
Yeah, or I can read them to you. And that way people get an idea of what's the question, what's the answer. So let's start from the top. Anshul asks, is cluster autoscaler the preferred way over the autoscaling provided by cloud providers?
Yes. So I already typed the answer while Mon is talking. So actually, the cluster autoscaler, sorry that we only actually cover HPA, and it seems like we will actually, as I said, everything is open source that we will share or experiment online, and we will keep on continuously updating with the VPA and the cluster autoscaler as well. And hopefully we get another opportunity to speak and share more experience about using these autoscaler solutions. But To answer Anshu's question, so thank you for the question. So the cluster autoscaler is usually built on top of these native autoscaler provided by these cloud service providers. So for if you look at the cluster autoscaler for AWS, that is usually built on top of the ASGs in AWS, meaning that the cloud formation or the Terraform file it already creates the ASGs on AWS for you, and that will be something that the cluster autoscaler leverage to scale up and down your clusters.
Second question, also from Anshul. Are there some best practices that should be followed when using cluster autoscaler? We're using cluster autoscaler currently, and some of the pods, such as Istio, get killed during scale down.
Yes, and unfortunately, this is a generic problem when you actually specify one dimension threshold, because this you can imagine, right? This is not a one dimension thing that the specified CPU threshold. Even in this HPA talk that we give, we actually have to combine two dimensions together. Same thing I think apply to CA, although we didn't have time to go over the CA concepts. But if you only scale up and down your cluster based on CPU, of course, it's very complex in the Kubernetes world, right? You may have different resources. It may be a hybrid, like heterogeneous cluster that you have some node with GPU capability, some node doesn't have GPU capability. But it happens that the GPU node actually has a very low utilization of CPU, which meets your criteria to scale down your cluster. Does that mean you should scale down the cluster? What if you actually want to run some GPU heavy workload like the machine learning workload? Where are they going? So these are the things that you have to have a multi-dimensional system help you to actually decide in a more comprehensive way to decide which node should be the best candidate to scale in if there's any opportunity, right? Just not a single dimension thing.
Okay. Next question from Patrick. Does Helm support the autoscale parameter right now, or do you need to use kubectl directly?
So the answer is definitely you can specify your Helm template YAML. You can have the min replica, max replica, target utilization, everything in your template, and you can when you do the Helm deploy, you can actually populate these values. So the answer is yes.
Okay. Next question. Wow. From Anshul. In HPA target utilization, let's see. Oh, is the HPA target utilization, is it based on request or limit parameters of pods?
So Mon, you want to take this?
Yeah, these are all based on request. And this is the same with VPA. It's also request-based, because request is a way in Kubernetes for your guaranteed resource. This is especially for CPU. You have the CPU. You have the container secret runtime, and to make sure that. So yes, it's all based on request.
Okay, thank you. And one last question from Patrick again. Can a pod get evicted move because of vertical scaling? Is that configurable?
So I think there's an ongoing effort to make VPA non-disruptive. So yes, this is right not there yet, but
yes. Sorry, go ahead, Ellen.
Go ahead, Man. We can also share the effort that is being done in the upstream Kubernetes to make VPA more less disruptive.
Yes, I think eventually VPA is going to be non-disruptive, but for now it is. I believe because if to make it a non-disruptive, the change in the scheduling side of is needed, and which really needs a lot of due diligence and work to make sure everything goes smoothly. So that takes, I believe, a little bit longer. Exactly when it's going to be done, I am not sure. And I do see some open questions.
Yes, we have some new questions if you're ready for them.
Yeah.
The first question from Tommy is, do you experience issues with production, with horizontal autoscaling in production on Kubernetes, particularly in metrics?
Yes, the question is if we experience any issues with production grade HPA in Kubernetes, especially with multiple metrics. I'm not sure what you mean by production grade. The HPA implementation we use is just from the community. And as far as our experiments goes, everything is working according to design. In terms of multiple metrics, you can supply any metrics that's supported by HPA. Basically, you can supply the default metric server. You can have your own custom metric server. There are many third-party metrics providers. You can also, someone uses the custom metrics, is using the QLens. Someone uses QPS. You can even combine them together, as I've shown in our last experiment. So I don't see any issues. I didn't see any issues, at least with our experiment.
Okay. And I'm going to actually answer his follow-up question because he needs a link there. So, oops. Okay, there we go. So then we're going to move on to Alex's question. Regarding the vertical autoscaler, vertical pod autoscaler, whenever the problem of disruption is solved, the pod is no longer, hold on a second, let me reread this because I'm not quite following this question.
So I think
okay,
Alex,
I'm just going to go on to the second. Yeah, go ahead.
No, I think Alex is interested to know why we need both a VPA and HPA, if I understand correctly. I think since HPA seems working fine, why we don't just use HPA, instead we want to use VPA, assuming that VPA is also non-disruptive. So this is I hope I understand you correctly, Alex. So this is a great question. So, but in fact, I think a lot of times, so for example, I think when you're eating a Oreo cookie, right? Do you really need the cookie every time you want a new cookie, or you really want just to eat the cream? For me, I just want the cream. So in that case, if you can give me more cream without the biscuit, that's exactly what we want. So this is the similar concept as VPA versus HPA. If I would just want more vCPU, but you just give me more CPU. If I just want more memory, just give me more memory, right? So it doesn't have to be like every time if I'm congested a CPU that is making my performance degraded, you always make a copy that will always make a replica of the memory usage as well, which is going to waste the memory, which I would throw the cookie away. I just want the cream, right? So in that case, I think there's certain use cases. I think in the upstream documentation, I think a lot of times that you see they want to have VPA mostly use cases is about database application, and HPA is for other application, web server applications, things like that.
Right, VPA is I guess the design, the best use case would for the stateful pods, right? HPA would be stateless pods, which you don't care, it gets killed and it can be spin up somewhere else, doesn't matter. VPA is like for more mission critical long running services, which is monolith, for example. That could be an example. Other use case could be, for example, you can run a Spark executors in the Kubernetes cluster, and you can initially give it a very, very small amount of resource. And when the load comes, you can decide to vertical scale, because this also applies to scientific computation, where you have, for example, MPI application or machine learning applications, where you don't want your executor to be killed. You want it to be there, but you want it to scale up and down based on your workload. Hope that that's helpful.
Thank you very much. And so then there was a request in there for a link to the source code again. So if you just want to paste that in to the Q&A.
Which one?
Kenneth is asking about a link to the source code. So if you can just go ahead and paste that in.
Yeah, so Mon, can you actually copy and paste the testbed we have with Kenneth?
Sure.
Yeah. Yep. Okay. And that looks like.
Yeah, Josh, I just noticed that Tommy has a question that actually related to
Okay.
ActiveMQ. QDAS.
Okay.
I see you also send a link about configure autoscaling custom metrics.
Yeah.
So that's the configuration part. But based on my experience, the queue management is usually complicated because the queue itself congested. For example, that doesn't mean that this is the root cause of the problem, because, for example, in Kafka, just similar to ActiveMQ, for example, if you have in Kafka, you have different topics that is belonging to different consumer to consume the queue. So if you actually see the queue size is very congested, that usually means there's some problems with the consumer side that is not processing the queue, the task that is fast enough. So when you talk about the performance and you want to apply HPA on the queue, like ActiveMQ or messaging queue application, you need to be extra careful about that, because that usually don't solve the problem directly. You need to look at the consumer side, see if there's some bottleneck on the consumer side that slow down the process of the queue message. And we are happy to discuss with you more on this. I hope that helps.
Okay, I think that's all the questions that we have. I don't see any others in there. So thank you very much, Meng and Enlin, for this presentation.
Thank you everybody for attending this.
Yes, thank you everybody for joining us today. The recording and the slides will be online later today. And we look forward to seeing everybody at a future CNCF webinar. And there's one later this week, in fact. So happy to share lots of information and technical expertise with you. And thanks again, Ming and Enlin, for sharing yours.
Thank you very much.
You're welcome. Happy Tuesday. Bye.